Hello, welcome to this course Transportation Network Analysis. I am Hemant Gehlot, a faculty member in the Department of Civil Engineering at IIT Kanpur. So, this course will cover the mathematical foundations for the analysis of transportation networks. Transportation networks are of various types. For example, the simplest one which everyone would have encountered are the road networks. We also have logistic networks which are responsible for the movement of goods across various parts of the cities. We also have transit networks which are responsible for the mass transport of movement across various places in the cities, and these transportation networks are useful for the movement of people, goods and services, and therefore it is important to study them to analyze different problems that arise related to these transportation networks. Many fundamental problems related to transportation networks arise in the real world. The most common problem that everyone would have encountered is of the shortest path problem. Here the objective is to find a path between two given places which offers the shortest travel time. It might seem that this problem is very trivial if the number of paths that are available between the two given locations are just few. However, this problem becomes more complex if there are too many paths between the two given locations, and there might be a lot of overlap between different paths between the two locations, and in that case finding the shortest path may not be such a trivial problem. So as we'll move along in this course, we'll be understanding how to find the shortest path for such complex networks. Another problem where the transportation networks are useful is how does traffic gets distributed among various paths or routes between two locations. See an example, let us consider this case where we have an origin and a destination in this figure, and we have three routes. Now a trivial solution might be that everyone should take the path that offers the shortest length. However, there can be an issue with that. If everyone decides to take the path that has the shortest length, it might get congested and it might no longer be path that offers the shortest travel time, and therefore this problem cannot be just solved using these trivial or naive solutions. To understand this problem further, let us consider an example here. We have an origin and a destination represented by these nodes 1 and 2, and suppose 20 travelers want to travel from node 1 to node 2. Here there are two choices of the paths that can be chosen. The first path offers the travel time which is given by this function 10 plus 3x1, where x1 is the flow which takes place on this first path, and similarly we have the travel time function for the second path which is given by 15 plus 2x2, where x2 is the flow that takes place through path 2. We can see that the travel times are proportional to the respective flows, and that is intuitive. As more and more flow will occur through a path, the travel time should increase. So let us consider one possibility. Suppose that all the travelers decide to take the top path. So in that case, the travel time that will be experienced by all of the travelers will be equal to 10 plus 3 times 20, which will be 70 units. Now let us consider another possibility. Suppose everyone decides to take the bottom path, that is x2 is equal to 20 but x1 is equal to 0. So in that case, the travel time that will be experienced by the travelers will be equal to 55 units. Now it can be seen that these two are not the only options that are available to the travelers. In fact, there are infinite such solutions if we allow the flow distribution to be continuous across these two paths, and the question then becomes which solution out of all of these solutions is the best one. Now let us consider a situation where 9 travelers take the top path and 11 travelers take the bottom one. So in that case, the travel time that is experienced by both the types of travelers is equal to 37 units, because the travelers which will be traveling on the top path, they will be getting this travel time of 10 plus 3 times 9, and the travelers which will be taking the bottom path, they will be experiencing the travel time of 15 plus 2 times 11. So both of these values come out to be 37 units. And in this case, we can see that this option offers the least travel time as compared to the first two options that were there. And it can be seen that in this case, the travel time that is experienced on both of the paths here is the same. So there is no incentive for any traveler to change his or her own decision. So we will be interested in solving these kind of problems as we go along in this course. This was a very simple example for which we can find out what is the best solution. However, when the network becomes very complex, we have a lot of paths between the origin and destination nodes. Similarly, when there are many origin destination pairs and there are these overlapping paths between different origin destination pairs, then this problem might not be that easy to solve. And the objective of this course is to understand how to solve problems for such complex networks. Another interesting problem that arises in the aspect of transportation networks is that is it always beneficial to construct a road, keeping in mind that the total system travel time across the network will reduce. Contrary to intuition, it may not always happen. So here we have two figures shown. So the original network just have 4 links AB, AC, BD and CD, and in the right side there is a proposal to construct an additional link which goes from B to C. It just happens that every time it might not be beneficial to construct a road if the objective is to reduce the total system travel time, and we will be understanding why that might be the case. And the reason behind this, which can be given at this level, is that we are interested in optimizing this system level objective, which is to minimize the total system travel time, whereas the travelers are interested in minimizing their own travel time. And because of this conflict in these two targets, it might happen that sometimes if a road is constructed, it might not always lead to reduction in the total travel time. This phenomenon is called Braess paradox, and we will be studying this paradox in more detail as we will go along in this course. Another very interesting problem that arises in the area of transportation networks is the following: that if a person is at a particular place and he wants to visit a given set of places and he wants to come back to the original place, but that too in the minimum time. So he wants to construct a shortest tour between a set of places. So the target is to find that shortest route. This problem is called traveling salesman problem. It is a very important problem that arises in the area of transportation networks. So in this figure we have 4 nodes A, B, C and D, and it can be seen that there are multiple tours that are possible. For example, one tour that is possible is to go from A to B, then B to C, then C to D and then D to A. However, there are other possibilities as well. For example, one can go from A to C, then B to D, then back to A. Okay, so out of all of these, which one offers the shortest length? That is the question. For this example, the tour that offers the shortest length is the one which goes from A to B, then B to C, C to D and then D to A, and its length is equal to 10 units. Now it might seem that this problem is very trivial for this example, because right now we do not have that many number of paths that are available. However, this problem becomes more complex if there are large number of nodes that are present, and in that case even listing down all of the possible tours may not be very practical in some cases, because the number of tours that exist can increase exponentially with the size of the problem. So in those cases we require that we systematically develop a method to solve this problem. Traveling salesman problem, which is also called in short TSP, has several applications ranging from not just routing and logistics in transportation, but also in the manufacture of microchips. Another very interesting problem that is closely related to the traveling salesman problem is related to the vehicle routing problem. So suppose we have a set of customers that need to be served by a fleet of identical vehicles, and the constraint is that these vehicles have a limited capacity. So for example, they cannot carry the number of goods beyond a particular number, and initially it is given that all of these vehicles are located at a given depot. So the objective of this problem is to find a set of routes for the vehicles that offer the shortest total time. So here you can see that there are these 3 tours which are shown here. In the center we have a depot node, So all of the vehicles are located there. These circles are the places that need to be visited. You can think of them as different customers whom these goods need to be distributed. So the question is that since a single truck cannot carry all of these goods that need to be given to all of these places in one go, so we need to have these different trucks. Now the question is that how should these different places be clubbed together so that a single truck provides goods at these places, and furthermore, once we allocate a set of places to a given truck, in what sequence should this truck visit these different places? So these two decisions overall should be such that the length of these three tours that we see here, that should be minimized. Okay, so this problem is called vehicle routing problem, as I mentioned. It has direct applications in the real world. For example, this arises almost frequently in the logistics area, because whenever the transportation of goods has to happen, so the companies that are responsible for doing this transportation, they have to decide how to group together different locations for transportation of goods and in what sequence should these trucks visit them and so on. So all of these problems that we saw, starting from the shortest path problem to traffic assignment, and then later we saw traveling salesman problem, vehicle routing problem, all of these problems can be tackled systematically if we mathematically represent them. And as I mentioned before, why there is a need to mathematically represent them? Because once these problems become large, then it is not possible to solve them using some trivial methods like listing down all of these solutions and so on. And the objective of this course is to build foundations to develop and analyze solution algorithms for solving large scale transportation networks. So this was the course overview, and now we will be starting to discuss the main content of the course. So the idea until now was to provide the motivation for studying this course. So all of these problems that we saw can be understood as different optimization problems. For example, the shortest path problem had the objective of finding the path that was having the shortest length between the two given places. Similarly, the traveling salesman problem, the objective is to find the tour that offers the shortest length and visits all of these given set of places. So therefore, it is important that we have a good understanding of optimization problems. So let us start to discuss about optimization. So optimization is the study of how to quantitatively model the choices that should be made to best achieve some objective. Every optimization problem will usually have three parts. The first part is the objective function. So this is a single quantity that should either be maximized or minimized. For example, in the case of the shortest path problem, the objective function was to minimize the length of the path that we find between the given set of places. There can also be optimization problems where the objective is to maximize something. So we will see examples for that also. Another important part of an optimization problem is the decision variables. So these variables are used to control the decisions in order to achieve the objective. For example, in the shortest path problem, the decision variables will be which path to choose. So using these decision variables, we can make some decisions, and then we can choose that option which offers the best objective function value. And the third part of an optimization problem is the set of constraints. So these constraints are any restrictions on the decision variables that must be obeyed. An optimization problem will always have an objective function and decision variables, but it may or may not have constraints. So if an optimization problem does not have constraints, it is called unconstrained optimization, and if it has constraints, then it is called constrained optimization. So for example, in the case of traveling salesman problem, one constraint that was there was we wanted to find a tour that should visit all of the given set of places, and it has to come back to the original place. So that was a restriction that need to be ensured. Okay, so let us look at some examples of optimization problems, the target here will be that we will try to see how can we mathematically represent the different physical problems that will be shown. And once we have a good understanding of how to mathematically represent different physical problems, then we will be discussing later different solution methodologies. So, let us consider this first optimization problem, which is a fence problem. Suppose we have 60 feet of fence available to us and we wish to enclose the largest rectangular area that is possible using this fence. So, the question here is, what dimensions should we choose for the fenced off area? So, let us represent the length of the rectangle that we want to achieve by L and the width of the rectangle by W. So, the objective function then is to maximize the area, that is equal to L times W. Now, note that it is given to us that the total length of the fence cannot exceed 60 feet. So, that is a restriction to the problem, that is, it is a constraint. So, we need to represent that constraint in a mathematical form. So, the perimeter of a rectangle, as we all know, is given by 2 times L plus W. So, this constraint can be expressed in this form that 2 times L plus W should be less than or equal to 60. And also we have this restriction that the length and the width cannot be negative. So, that is why we have L greater than or equal to 0 and W greater than or equal to 0. So, with this we have now discussed what is the objective function, that is L times W. We had also defined what are the decision variables in this problem, L which is the length of the rectangle and W which is the width of the rectangle. And then we saw these different constraints that will be there. First constraint, that the total perimeter cannot exceed 60 units and the length and the width should be non-negative. So, we can put together this information in a systematic way. So, this is the way we actually represent this information. Since this optimization problem is a maximization problem, we write it as max LW. Now, you can see that L and W are written below this max operator. So, that is because to tell that L and W are the decision variables in this optimization problem, and it may happen that sometimes we may not put the decision variables below the max or min operator, but usually the convention is that we should put it. So, that is why in case if you see any time that you have some decision variables below the max or min operator, so it is just to highlight that what are the decision variables in the optimization problem. And we have these constraints put together here. You can see that there is this S dot T dot that represents subject to. So, all the constraints come after this subject to. So, this is saying the same thing what I said. So, decision variables are indicated underneath the word max. If it would have been a minimization problem, then instead of max it would have been min, and S dot T dot stands for subject to, as I told before. Okay. So, let us consider another optimization problem. So, this one is the shortest path problem which we had initially discussed. So, let us now discuss it more systematically. So, in this figure that is shown here, we have one origin node and we have one destination node. Let us represent the set of all of the links in this network by capital A and the set of all of the nodes in this network by capital B. Let us represent the origin and destination nodes by R and S respectively. So, it can be seen that this is the origin node and this is the destination node. So, let the travel time on any link A be represented by TA. So, now we represent the decision variables. So, we will represent XA to be a binary decision variable. It will either take value 0 or 1 for every link A. It will take the value 1 if link A is part of the shortest path or shortest route and 0 otherwise. Note that I will be using the terms path and routes interchangeably in this course because they mean the same. So, once we define that XA is a binary decision variable and it takes value 1 if link A is part of the shortest path and 0 otherwise, then we can represent the objective function of this optimization problem in terms of summation TA XA, where summation goes over the set of all the links capital A. So it can be seen that if a particular link A is not part of the shortest path that you select, then xa will be equal to 0, and therefore no contribution of travel time for that link will come into consideration in this summation that is there. So only the links that are selected in the shortest path will have xa equal to 1, and for them we will be summing up the travel times in this summation. Now one trivial constraint that exists is that xa, the decision variable that we have defined, is binary. So it can only take value 0 or 1 for every link A, and we also require that xa values form a contiguous path which starts at the origin R and ends at the destination node S. Now why is this important? Note that if we do not put this condition that the final path should be such that it actually joins the given origin and ends in the given destination, then it can happen that you can get xa values to be 1 such that there can be some links which are arbitrarily having xa equal to 1, but they do not form a continuous path which starts from the origin R and ends in destination S. Okay. For example, suppose this link has xa equal to 1, similarly this link has xa equal to 1, and this link has xa equal to 1. But these three together will not form a path that starts from the origin node and end in destination node, because there is no way you can connect this link with this link directly, because these links, for example, which connect them do not have xa equal to 1. So that is why we need to have a condition that the xa values that come out at the end of solving this optimization problem should be such that this final path in fact joins the origin node and is a continuous path and ends in the destination node. So in order to do that, let us first define some notation here. Let capital OJ denote the set of links that leave node J. So for example, for the origin node, these two links are the one that belong to the set OJ of this node J. Similarly, let us define this set IJ to be the set of links that enter node J. So for example, if you consider this node, then these three links here are the ones which enter this node J. So they will belong to the set IJ of this node J. Why we are using this notation O and capital I? Because you can also think that OJ is the set of outgoing links from node J, and similarly IJ is the set of incoming links from node J. Now we will be considering 4 cases. The first case is that a node J does not lie on the shortest path at all. So in that case, the xa value should be 0 for all of the links that enter that node J, and it should also be equal to 0 for all of the links that exit that node J. And why is that? Because you can see that, for example, this was the path that we finally selected. Now if you consider, for example, this node here, then there is no link which is entering this node J and has been selected in the path that I mentioned before, and similarly there is no link which is exiting this node and that was selected in the path that I mentioned. So therefore for such nodes we will have all the links, whether they are incoming or outgoing to this node J, they will have xa equal to 0. Then let us consider another case where node J is lying on this path that we finally selected, but it is not the origin or the destination node. So for example, suppose this is the path that we finally selected, and let us consider this node here. Now for this node there will be exactly one link that will belong to the set of outgoing links from this node J that will have xa equal to 1. In this case it will be this link, and similarly there will be exactly one link which will belong to the set ij of incoming links to this node J that will have xa equal to 1. So in this case this will be this link. Now the case 3 is that when this node J is the origin node. So in this case we will only have one outgoing link exactly that will have xa equal to 1. So if this was a path that we finally selected, then this is that link which is outgoing from origin node and has xa equal to 1. And similarly, if we have node j to be the destination node S here, then there will be exactly one link which will be incoming to this destination node, and it will have x equal to 1. In this example, this is that link. So, a destination node will never have an outgoing link, and an origin node will never have an incoming link. That is why we have considered these cases 3 and 4 separately. So, we will continue this example in the next lecture. Thank you.